Welcome. In this video, I'm going to be working Algebra 2 Homework 8.3, and we're going to be graphing some radical functions and also solving some radical inequalities, so that'll be nice too. Okay, so we're going to start with a couple of problems. It's like, hey, here's a graph, write an equation that could represent the graph. So maybe I'll zoom out to show both of them. Both of these are going to be square root graphs because we're really only dealing in square root and cube root graphs right now. And cube root graphs, their domain doesn't just start or stop somewhere. We can put anything we want into a cube root equation. So this one, because it starts over here at x equals -2, I know this is a square root equation. So kind of my skeleton is y is some number times the square root of x minus some other number. And I think in class I probably called this like x minus h plus k, where h and k was the point where the graph started or stopped. Okay, so in this case, I've got h and k equaling -2 and -4. So I've got -2, -4. So I'm going to just kind of plug in x minus -2 plus the -4. We can write that a little nicer. We can say y is equal to some number times the square root of x plus 2 minus 4. And then we'll solve for that number using some other point that's given to us on the graph. And in this case, that's going to be -1, -3. Okay, so I'm going to use x equals -1 and y equals -3. So -3 is going to equal a times the square root of -1 plus 2 minus 4. And maybe, I mean, if you're sitting there saying like, dude, it went over 1, up 1, so a is going to be 1, then great. Wonderful. Good for you. Okay, if you're not seeing why that's the case, then just solve it out for a, and you'll see that a is going to be +1. Add 4 to both sides, get 1 equals a times the square root of 1. Okay, a equals 1, and so y equals the square root of x plus 2 minus 4. Okay. This next one. Okay, I'm going to do the same thing. This is a square root because the graph only starts there at x equals 0. Okay, so I'm going to start with my skeleton. Y is some number times the square root of x minus h plus k. Okay. In this situation, h and k is going to be 0 and 3. So I'm going to plug those in. I'm going to say I'm going to use the other point to solve for the value of a, though. So the other point is 9 and 0. X is 9, y is 0. Okay, so I'll plug those in. X is 9, y is 0. So 0 is some number times the square root of 9 minus 0 plus 3. Okay. So 0 equals a times 3 plus 3. So I'd say -3 equals 3a, and a is -1. So my equation is y equals negative square root of x plus 3. You can also write that as 3 minus the square root of x, however you want. Okay. Okay. Now with these, we're going to match the function with the graph. Okay, I like these. So what we're going to mainly be doing is I'm going to be matching based on the edge of the graph. Okay, and I'll just highlight all of those with red. I was kind of using blue for that in the previous problems, but it'll be all right. These are all in different spots, so I think I'm going to be able to use that. Okay, for instance, I'll just start with a. This is at where x is 0 and y is -3. So I'm expecting the square root of x minus 0 minus 3, right? So square root of x minus 3, that's number 6. I'm looking for a. All right, so a there. The domain of this thing, okay, the x values that I can plug in and get a y back is just where x is greater than or equal to 0. It's also just the x values that I'm seeing on the graph. So x greater than or equal to 0. And then the range, the y coordinates that we're seeing, if I clear all this out, we're seeing y equaling -3 right there at the bottom. And then the graph's going up, so it's all the y's that are greater than or equal to -3. We could also say that, okay, well, the square root of x is either going to be 0 or a positive number, and so I'm either taking 0 or a positive number and subtracting 3, so the very least that would be -3 if I was taking 0 minus 3. Okay, But then the rest of these I'm going to go a little faster through. B, I'm at x equals negative 3, y equals 0, so I'm looking for the square root of x minus negative 3 plus 0. B number 3. Okay, so it'll be B. The domain is x is greater than or equal to negative 3, and the range is y is greater than or equal to 0. And I think domain and range on this one, if you're given a graph, it's just easiest to look at the x's and y's that we're given, right? Domain is x's, range is y's. So C, that's at the point 3 and 3. So I'm looking for the square root of x minus 3 plus 3. And that will be number 8 is C. This one, the domain was x is greater than or equal to 3, and y is going to be greater than or equal to 3 as well. D, that's x is 0 and y is 3, so I've got the square root of x minus 0 plus 3. It's number 4. Okay, in this one, the domain is x is greater than or equal to 0. And the range is y is greater than or equal to 3. All right, for E, that's going to be, okay, negative 3, negative 3. So I'm looking for the square root of x minus negative 3 minus 3. So plus 3 on the inside of the square root, that's going to be number 7. Uh-oh. Okay, number 7 was E. That means 5 will be F. 5 square root of x minus 3, yeah, because that's happening at 3, 0. That makes sense. Okay, for E, the domain is x greater than or equal to negative 3, and the range is y is greater than or equal to also negative 3. F, what do we got here? Domain x greater than or equal to 3, and range y greater than or equal to 0. Let's just that move it a little bit, yeah. Okay, solve the inequality. All right, so these, we're going to solve, like, nothing's wrong, and then we're going to go back into the very end, we're going to consider the radicand. And this is something that you'll do more in pre-calculus next year, but I thought it would be something, since we're studying radicals right now, it would be really good for us to start in on our study of radical inequalities here in Algebra 2, even if it's not the most important thing that we learn. I think the most important thing we're learning here is dealing with fraction exponents, solving the equations, sketching some graphs, knowing what they look like. And I think that's what's really important here. So I'm going to just kind of solve it this one. Try to isolate the square root. Say, all right, 7 square root of x is less than 8. Square root of x is less than 8 divided by 7. And that's okay. We can divide both sides of an equation by a positive number, an inequality by a positive number, and that won't reverse the direction of the inequality. I'm going to square both sides and get 64 over 49. Okay, so that would lead me to think, all right, well, here maybe I've got 64 over 49, and I've got everything that's less than it. Okay, that would be what I'm thinking is my solution. But then I need to also consider the radicand. Okay, so this square root of x, okay, this won't make sense if I plug in something that's less than 0. So I know also that x needs to be greater than or equal to 0. So I'm just going to say, all right, I think that's where x equals 0 is. And so I'm looking for the overlap of these two regions, which is going to be here. And that's going to be the set of all x's that are greater than or equal to 0, but less than 64 over 49. So I could write this as 0 to 64 over 49 as an interval, or I could write this as, that an inequality like that. Either one of these would be, like a perfectly valid solution. Hey, but the sketch itself is not going to be quite enough. All right, this next one here, we're going to pretty much do the same thing. Oh, except there's not going to be as much to consider because we can take the cube root of any number we like. So I'm just going to say, all right, 2 cube root of x, add 5 to both sides. That's going to be 8. Divide both sides by 2. Cube both sides. And we get, okay, x is greater than or equal to 64. But yeah, there's no restriction to what we can put in the to the radicand. There's no restriction to what we can put in cube root. So that's just going to be our solution. X is greater than or equal to 64. Okay, we could write it like this. We could write it as an interval from 64 up to positive infinity. It does not really matter. All right, with this one, I'm going to divide both sides of the inequality by -2, and remember that's going to reverse the direction of the inequality. I'm going to cube both sides. It's okay to, cube a negative number, but hold on a second. Let me think about this. Right, yeah, cubing both sides of the inequality is going to be fine because cubing preserves the inequality. Like if one number is bigger than another number and then you cube both of them, the bigger one's still going to be bigger. Yeah, so I don't need to worry about this. X plus 4 is greater than the cube of -6, so that would be -216. If you're unsure about that, come talk to me. I'd be happy to draw you some pictures and show you why that's true. So then I'm going to subtract 4, and I'm going to say x is greater than -220. Okay, yeah, so if I was going to draw a picture of that, it would look like that. If I was going to write it as an interval, it would be -220 up to positive infinity. Okay, but I think that first one would be probably the best response to the inequality. That's what I like best. All right, over here, the last of these inequalities, I'm going to start by dividing both sides by 5. Divided by 4 and getting 5, goodness. Okay, and then I'm going to square both sides of this inequality. Add 2 to both sides, and I'm going to get x is greater than 27. Okay, but then I need to consider the radicand. Okay, so I need x minus 2, okay, I'm glad I put one of these on here, is greater than 0, so that's x is greater than 2. Okay, well, it's like, well, if x is greater than 27, it's already greater than 2, so I don't really have anything to worry about. So that x is greater than 2 is not going to contribute anything to my solution. Something else I could say is that, okay, we're looking for the overlap of these two, and the overlap of these two is just going to be the same as what I had originally, which is where x is greater than 27. And so you could say it was the interval from 27 to infinity if you wanted, but you could just also say x is greater than 27, which is probably what you would arrive at first, right, if you're just solving the inequality. So I just recommend you stop there. All right, now we're going to be asked to produce some sketches of graphs of radical functions. Okay, and so this is probably, I think there's going to be more than just these three, or at least I hope. But I think this is good because we've got a good selection. We've got a regular square root here. And so what I'm going to remind you is that the graph of, just y equals square root x, or a regular square root graph, it kind of looks like that. And this point right here is where we're taking the square root of 0. Okay, so over here I need to figure out what x gives me. Okay, so I'm going to say x minus 1 equals 0, and that tells me x equals 1. Okay, so I know that x equals 1 is the x-coordinate where the edge of the graph is. And the y-coordinate would be f of 1, which if I plugged in f of 1, right here, it would be the square root of 1 minus 1, it would be 0, right? That was the whole point. I don't have anything added onto the outside, so the vertex thing would be over here at what I might call like 1, 0. Okay. And then it's going to go over here. Now we could probably do a little better than just that. We could label one other point to give us a sense of scale. Okay, because this is 1 times the square root of x minus 1, so I don't know, I might just choose some other point. I'll choose strategically. I'm going to choose x equals 2, because I know how to take the square root of 2 minus 1. So I would just point this point out and say that's x equals 2, y equals 1. Okay, and that would be a good sketch. Okay. The graph of a cube root function, that is going to look like that. Really what it is y equals x cubed turned on its side, and somehow upside down or something. Okay, so it's going to look like that, and the point here in the middle, which I didn't do a very good job of, but it's supposed to be like, vertical at that moment. That point right there, that's where we're taking the cube root of 0. That's our vertex point. So that's going to happen when x is equal to 0, and when I plug in 0 for g of x, I'm going to get 2 times the cube root of 0, and it's going to be 0, so this vertex is happening at the origin, so it looks like kind of a pretty standard cube root graph. That's going to be a little better. And if I was going to label one other point to give it some sense of scale, I would say, okay, we can take this cube root of 1, we can take the cube root of 8, we can take the cube root of 1,000, might not really matter. I'm just going to say over here, maybe this is 1, and the 2 times the cube root of 1, well, that would be 2. So I could label it like that. And that would be a good sketch of the graph. 3 minus the square root of x. All right, so I'm going to find the place where the, what am I saying, where the vertex is, because it's a square root graph. Okay, that's going to be where x is 0, and h of 0 equals 3 minus the square root of 0, and the square root of 0, there's nothing wrong with that. That's just going to be 3 minus 0, and that's 3. So my vertex point is at 0, 3. And it's going to be one of those things that grows, but, really levels off. Okay, really what it is parabola, part of a parabola on its side. And then I can give it, wait a second, that's not going to be right because it's 3 minus the square root of x. So I'm going to turn it upside down, right? And then, okay. What we could do is we could solve for this x-intercept, and I think that's what I'm going to do, but then I'll also show you what another thing that you could do. We could just say, okay, x equals 1, plug in this point here, x equals 1, that's going to give me 3 minus the square root of 1, so that would be 2. Hey, that would be another point, but I think it's good for me to, remind you about how we would solve for the x-intercept of this thing. So the x-intercept of h, it's going to be where h is equal to 0. So 3 minus the square root of x is equal to 0. And this picture's obviously not going to be drawn to scale. But if I solve for x, I'm going to get 3 equals the square root of x, square both sides, and I'd get x equals 9. Okay, so that's how I would find that. I think I just drew the square root curve like a little too steep. But that's going to be a sketch for us. Alright, the square root of 10x, that's going to have its vertex where 10 times x equals 0, and that'll just be where x is 0, and f of 0 would be the square root of 0. Okay, so it's starting here at the origin. And it's going to be kind of one of those curves. And I'll just pick out some other point. I really want to think is what's some number that I could multiply by 10 to get a perfect square? Okay, so it would be like at a grid intersection point, and that would be 10, because the square root of 100 is 10, so if I plug in x equals 10, I'm going to get y equals 10 over here, right? Yeah, because the square root of 100 is 10. And that would be it. That would be a good sketch. The cube root of negative x. Alright, so I'm gonna say I think you would know what to do if it was the negative cube root of x, and I am proposing that these two things are the same, but maybe by way of, a radical property, right? The cube root of negative 1 is negative 1, so this is the same as the negative cube root of x. So it's going to look like regular cube root, except upside down. And because, what had been up here and was positive, and down there is negative, got multiplied by negative 1. So I've got something looking like this and that. Get rid of that. And so that's going to be the cube root of negative x, or the negative cube root of x. Then h of x is the square root of 3 minus x. Okay, so I'm going to go back kind of old-fashioned ways. Okay, the x-coordinate of the vertex is where 3 minus x is equal to 0. And that's where x is equal to 3. And the y-coordinate of the vertex is going to be h of 3, which is the square root of 0, which is 0. Okay, so x is 3, y is 0. Okay, now... Okay, what should I say about this? The fact that it's 3 minus x, well, like if x was 4, that'd be trying to take the square root of negative 1, and we can't really graph that. So I need to be taking numbers that are less than 3, and if you think about it, if x is a negative number, then I'm taking the square root of something bigger than 3, because I'm subtracting a negative. So the domain of this thing, it's going to open the opposite way, is what I'm saying. What I might say, I might label this as the work to find the vertex. But if I consider the domain of this thing, okay, the square root function, okay, I've got to put in a number that's greater than or equal to 0. And, I could subtract 3 and divide by -1, which would reverse the direction of the inequality, but I could just add x to both sides, and I'd get x was less than or equal to 3. So what's going to happen here is the graph is going to open up back that way. And what was I going to say about this? Oh, we want to put another point on there. Maybe I'll just, label y-intercept this time. Okay, this isn't going to be like a nice number, but the y-intercept, that's where x is equal to 0, so that would be h of 0 equals the square root of 3 minus 0, so that's just square root of 3. And that's going to be my sketch for h. Now we're going to find the zeros of the function, and that's something that I did on one of those other problems when I was finding the x-intercept. So the zeros is just where y is equal to 0, so f of x is equal to 0, that's 4 plus the square root of x equaling 0. Square root of x equaling -4. Square both sides. Okay, so I'm going to need to check my answer, and x equals 16. And then I would say, okay, check my work. Is f of 16 equal to 0? That's 4 plus the square root of 16. That's 4 plus 4 is equal to 8, not 0. Okay, so that one's not a 0, so this one has no zeros. If I was to draw you a sketch of the graph, okay, this would just be like the graph of regular square root x, but moved up by 4, right? Because all of the y-coordinates got 4 added to them, and that doesn't have any x-intercepts. That never hits the x-axis, so it makes sense that I wouldn't be able to see anything there. Next, we've got 2 minus square root of 8 times x. So this one, that would make, I think this one should have an x-intercept, right? Because there should be some number where I can take the square root of 4. And that's really, that's one way you could think about this, right? Is that I need to be taking the square root of 4 in order to have 0. 2 minus 2 would be 0. And then that would be where x was a half, I think. So that's what I'm expecting to get back. But I'm going to solve this one, the way that we're familiar with. So if I'm finding the zeros, I'm solving the equation g of x equals 0. So 2 minus the square root of 8x equals 0. So it's 2 equaling the square root of 8x. Square both sides. I get 4 equals 8x. Divide both sides by 8, and I get x is 4 over 8, or x is half. But since I squared both sides, I need to check my answer, right? So let's say g of 1/2 equals 2 minus the square root of 8 divided by 2 is 4, and that is equal to 0, so that's good. Okay, I've got a 0. And for this one, okay, this is something that we're going to probably, deal with every once in a while algebraically, but not graphically. That's something that, I'll leave for pre-cal next year. Although these are really interesting functions, these things that have a square root of a higher power of x inside of them. We're not going to really be studying them this year. So, but we can find the zeros of this thing. So I'm going to say, all right, we're interested in where h of x is equal to 0. That would be where the square root of x squared minus 16 minus 3 was equal to 0, and so where the square root of x squared minus 16 was equal to 3, and if I squared both sides, I could do that. I just need to check my answer at the end. I'd get something that kind of whittled down to x squared equals 25, which would lead me to believe that x was either 5 or -5. Okay, and what was I going to say? Okay, I need to check my answers. But it does look like both of these are going to work, because if I square 5 or if I square -5, which is kind of what I got to start with, the exponents before the subtraction or then the square rooting on the outside, I'm going to get 25 minus 16 is the square root of 9 minus 3. That does equal 0. So these are both x-intercepts on the graph of h. And so I think what that shows you is that the graph of something like this is going to be significantly more complicated than what we've been looking at. But you might have a graphing calculator, or you definitely have access to Desmos.com. Just type that in and see what that graph looks like. There's definitely insights to be had from looking at the graph of this thing. there's two more that we're going to want to find the zeros of. So f of x equals 0, that's where the cube root of 8 minus x is equal to 0. Well, the only way that's going to happen is if I'm taking the cube root of 0, so that's just going to be where x is equal to 8. I don't think we need to, waste a whole bunch of time like cubing both sides, adding 8, or adding x to both sides. I think just look at that, solve that with our eyes, right? That if x is equal to 8, then we'll be taking the cube root of 0, and that's 0. And that's the only way we're going to be able to solve that equation. And this last one, looking for g of x equals 0. Okay, all cube root equations have at least one x-intercept. I'm thinking about that. I think it might be exactly 1 if it's just a cube root. But kind of like how all third-degree polynomials have at least one x-intercept. Those facts are, fundamentally related, but not what we're really talking about today. So I'm going to just solve this equation, set the function equal to 0. It is negative 10. I'm going to divide by 5. And I get negative 2. Then I'm going to cube both sides. That means I will not really be needing to check my solution. And I'll get x equals negative 9 when I subtract 1 from both sides, and then that'll be my x-intercept. If you wanted to check, you'd see that you were taking 5 times the cube root of negative 8 plus 10. Okay, that makes sense. I'd be having g of negative 9 equals 0. Alright, now something, this is a little old, I like that we're having this on here. The square root of x to the 9 halves. Well, that's like taking x to the 9 halves and taking it to the 1/2 power if I'm taking the square root of it, right? So I would multiply these exponents, and I would say that that is x to the 9 divided by 4. 1 over x to the 4, okay, x powers of x in the denominator, we just call those negative powers, so that's going to be x to the negative 4. And 1 over the square root of x, okay, well, I could say that's 1 over x to the 1/2 power. That's the thing that we learned somewhat recently. And if we've got that, just like before, we got that power of x in the denominator, we're just going to call that a negative power and say that's x to the negative 1/2. Alright, now on the last page we've got some more sketches that have a little bit more complexity to them. So I think what I'm going to do is I'm going to, with all of these, kind of solve for the vertex point that I was talking about, for a square root graph, the edge of the graph, or the cube root graph, like center of the graph, if you will, and then find one other point and then just kind of draw the overall shape. And I'm going to plot just a whole bunch of points on these. I don't think that's going to be the best use of our time. So I'm going to start by finding the vertex point. That's what I'm calling this. The edge of the domain. So it's going to be where x minus 3 is equal to 0. It's going to be x equals 3. And then y is going to be g of 3. And that's going to be 0 plus 2 is 2. So it's 3 and 2. Kind of label that point there. Right, then I can just take one other point. Okay, I can see that, it's going to have that multiplier is 1, so I could go over 1, up 1. That's one thing that you can always do. So look at the multiplier, go over 1, up by that amount, or down by that amount, if it was negative. But I'm going to plot a second point, and I'm just going to choose something that would cause me to take the square root of 4. So I just have like something a little more interesting. So that would be where x is equal to 7. So my other point is going to be x equals 7, and y is going to be the square root of 4 is 2 plus 2 is 4. But you could choose some other point if you wanted. 1, 2, 3, 4, 5, 6, 7, 3, 4. And that would be a suitable sketch for us. Describe the domain and range. Okay, well, now that I've already drawn the graph, it's pretty plain to see, but I think it would be good for me to go back in and be like, okay, the domain is what are all the x's I'm allowed to put in. Well, I'm allowed to put in to square root any number that's greater than or equal to 0. And so if I solve that inequality, I get x is greater than or equal to 3. Well, that makes sense, right? Because I'm seeing that this graph is only existing at and to the right of x equals 3. for the range, okay, it really has to do with that number and kind of something about that square root. Okay, back when we defined square root, it was a while ago, I think it was even when we were talking about quadratics, it was the positive square root. Okay, well, if you see the square root printed on the paper in front of you, which you do, it's in ink, that means the positive square root. So I've got this 2 right there that I've underlined in red, plus the square root, which is always a positive number, unless I'm taking the square root of 0. Okay, so the very least this could be would be 2 plus 0, or square root of 0 plus 2. And so the very least y can be is 2, because y is g of x, and so that's where we're going to say y is greater than or equal to 0 plus 2. And the reason for the 0, I think, will be more obvious when I do a couple of other examples. Okay, this one, b of x is the cube root of x plus 4 minus 5. Now, what I'll say about domain and range, for cube root functions, it's always all real numbers, at least in this class. Domain is the set of all real numbers. The range is the set of all real numbers. We just won't even worry about that. We'll just try to graph the thing. Okay, so the center point, the vertex, would be where the x-coordinate would be at where x plus 4 is equal to 0. So that's going to be x equals negative 4. The y-coordinate of the center point is going to be, well, whatever I get when I plug in negative 4 for b of x. So b of negative 4 would be the cube root of 0 minus 5 would be negative 5. So we go over here to where x is negative 4 and y is negative 5. Okay, that's going to be kind of the center point. We know how to take the cube root of, 8 and negative 8 really well. That's kind of like before I was choosing something that wasn't just 1. So, because if I did, it would just look like, okay, I go to this point and that point. Whoops, is that even right? No. That point. And I go and I make it look like that. Well, that's not really enough to fill out the graph, the whole field. So I'm going to go and look for something that causes me to take the cube root of 8, because that's what I'm good at. So I'm going to say x equals positive 4, y equals the cube root of 8 is 2, minus 5 is negative 3. So that's x equals 4, 1, 2, 3, 4, and then y equals negative 3. All right, here. So that means that I can go, and I know it's vertical for a moment. Oh, that was pretty rough. But that's why I don't like sketching on these. On these grids where you have to fit it in perfect, and there's that pressure. I don't even know how far this goes over. 5, 6, 7, 8, 9, 10. I can't even go over where I'm taking the square root of negative 8, so I just got to go to here and just do the best I can. And it's like that, and that's a pretty rough sketch, but okay, that's the best I can do. Okay, let's just move on. This one will be a little better. So the vertex will be happening where x plus 1 is equal to 0. That's where x is negative 1. H of negative 1 would be negative half of 0. Okay, so it's just right here. And then some other point I need on there would be, I don't know, some number that I could add 1 and take the square root of. Then also want to divide that square root by 2. So I think it's going to be like, I'm going to be having to take the square root of 4. Because I can't get the square root of 16, I'd have to have x equals 15. I don't think I have enough tick marks on this graph. So I'm just going to choose x equals 3. And that will make y equal negative 1/2 of the square root of 4. So that's y equals negative 1. Yeah. X equals 3, y equals negative 1. And then I connect it with one of these parabola-looking things. And I've got myself a sketch. That's pretty good. So for the domain, I think about what can I plug in there. That's x plus 1 is greater than or equal to 0. And I solve that inequality. X is greater than or equal to negative 1. And that does make sense. I'm saying negative 1 right there. The graph is only existing to the right of it. The range is going to have to do with, the number that's added onto the outside, which there isn't. And, the idea of the negative 1/2 times the square root. So the very greatest that the square root, or pardon me, the very least that the square root is 0. But otherwise it's a positive number. So I've got this negative half multiplied by a positive number. So, the bigger the positive number gets, the more negative h of x gets. So I know that h, or the y coordinate, is going to be less than or equal to 0. Okay, that does make sense, right? We're seeing that the graph is going down the farther I go to the right. Okay, it's not going very fast, but it is going down. So the range is going to be the set of all y's that are negative. So if I wanted to find, some place where h of x was, say, negative 100, I just need to find some number that I could, some really big number that I could plug in, and I'd take the square root and I'd get positive 200, right? So that'd be some huge number, but I could find it, and you could go down as far as you wanted. You could make y as negative as you wanted. Right, negative cube root of x plus 1. Okay, that'll just look like regular cube root made negative. But I might, I think I've got room for 8. 2, 4, 6, 8. Down by 2. Yeah, I'm going to do that. 2, 4, 8. Up by 2. Oh, but that needed to be 1 up like that. Yeah, that'll be better. Alright, so alright, that's the best I can do. It's kind of hard, That didn't look very vertical in the middle, but I tried. Okay, so the domain and range of both of these is going to be, domain, because it's a cube root function, is the set of all real numbers, and the range is also the set of all real numbers. Right, we got a few more of these. The negative square root of 2x, and that's going to be different from the square root of negative 2x. Okay, the way that looks. So I'm going to say the vertex of this thing is going to be where 2x equals 0, that's x equals 0, and if I plug in x equals 0, I'm going to get y equals 0, so it's going to work like that. Okay. The fact that we're multiplying on the outside of the square root means that, f is going to be negative of whatever it would have been had I not. So f is going to be coming back negative a lot, so it means I'm going to have y coordinates that are negative. Okay. So if I think about, taking the square root of 9, that's probably not the best example. Maybe taking the square root of 16. Okay, my other point would be where x equals 8 and y equals the negative square root of 16. Okay, well, that's negative 4. So 1, 2, 3, 4, 5, 6, 7, 8 in x and negative 4 in y. Okay, that gives me some room to draw a graph here. And there we go. That's going to be, my square root curve. It's kind of upside down because of that negative on the outside. It's a little steeper than usual because of that 2 on the inside. And I think that'll be a suitable sketch for us. Got the kind of vertex point labeled, one other point accurately plotted. That'll be enough. Okay, for the domain, let's solve for that. I'm going to say, okay, the thing on the inside of the square root needs to be greater than or equal to 0. So that's going to happen when x is greater than or equal to 0, and okay, we're seeing that right here. That does make sense. Okay, the range, again, kind of like the last one I solved on, has to do with the fact that there's nothing on the outside. Well, the very least that the square root can be is 0 right here. And otherwise, the square root is going to be positive, and then multiplying it by -1, so it's going to be the set of all negative numbers, so it's y is less than or equal to 0. It's actually easier to understand on some other ones. Okay, but that's going to be the range there. And we're seeing that the graph is only existing below the x-axis. Alright, 3 times the cube root of negative x. I feel like we already graphed one that was like this, because I already said that you can factor out the negative negative 3 times the cube root of x. And so I'm just going to work this one really quick. Now it's going to go down 2, 4, 6, 8. So go down by 6. 1, 2, 3, 4, 6. Oh, this one's not very good. But you get the picture. So I go over to negative 8, up by 6. Okay, that's not terrible. And then just like all the cube root ones, the domain is all real numbers. And the range is also all real numbers. All right, good. I'm glad to see that that happened. I'm going to solve for the domain first on this one, just to so we have a good idea of what's about to happen. Okay, so the thing on the inside of the square root, that negative 1/2 x, that's got to be greater than or equal to 0. So to get rid of that negative half, to get x on its own, I got to multiply both sides by negative 2. Now that's not going to change the 0, but it is going to reverse the direction of the inequality. Because 0 times negative 2 is 0, but multiplying both sides of an inequality by a negative number, that always reverses the direction. Okay, so my domain is going to be x is less than or equal to 0. One thing that does mean is that 0 is going to kind of be like the right edge, or that's going to be the x-coordinate of my vertex, right? And then a of 0 is the square root of 0, okay, so it's going to be right here at the origin. The range, well, it's just the positive square root plus nothing, so the range should be y is greater than or equal to 0. Okay, what's going to happen here is that the graph is going to look mostly the same, it's just going to be happening a little slower, okay, and it's going to go backwards. So negative half x, we got to think about, okay, what's a number that I could divide in half and take the square root of? Okay, maybe 8. So if I've got x equaling 8, then that would be y equaling a of 8 is, nope, not 8, negative 8. I was envisioning 8 over here to the left. Would be the square root of 4, and that's 2. So 2, 4, 6, 8, up to 2, and then, okay, I'll just kind of fill that in. And then we see that, okay, the way that that graph is going, y is, you know, we're going to cover all the positive y's eventually. It's going to take a while because that graph is growing super slow, but, you know, it is going up as I move to the left. All right, last one here. So h of x is a cube root function. So that means that the domain and range are going to be all real numbers. Okay, if I want to find the kind of the vertex point on this thing, then I'm going to think about what x makes me take the cube root of 0. That's going to be x equals 0, and h of 0 is equal to 2. So I go and I plot the point 0, 2. And then, you know, cube root of half of x. Well, I might say, all right, well, what's a number I want to take the cube root of? 1. Can take the cube root of 8, but I don't think I can't put in x equals 16, so I'm just going to have to plug in x equals 2. So if x equals 2, h of 2 is going to equal cube root of 1 plus 2, and that's equal to 3. So 2, 3. And then I guess I need another point on the other side, but I could do x equals negative 2. Because then I'd be taking the cube root of negative 1, and that's pretty easy also. That's negative 1 plus 2, and that's going to be negative 1. Wait, no, that's positive 1. Negative 2, positive 1. Alright, so I'm drawing a graph here. That was pretty okay. Alright, but I think that's all the graphs for this video. Yep, that's all of them, so thanks for watching.